Hi everyone, and welcome to this video on ensemble methods. And in particular, we're going to be looking at bagging and pasting. They're very simple concepts, as you'll see. As I said in the bias and variance video, everything's simple to start with, and then there are all these nuances. And I'm doing kind of the simple gloss over the nuances or even the various formulas and just give you kind of the gut level understanding of how these algorithms work. That's sort of the essential first step in all this. So there's more complexity, but I want you just to get a basic idea of bagging and pasting. And the question I'd like to ask to start this discussion is, what did the person in the first slide look like? So I've been showing pictures of young people, and I want to know, hey, what do you think that first person looked like? Can you describe some features about that person? And let's say this is Anne right here, and she says she thinks that person had glasses, headphones, and short hair, and it was a guy. He was sitting at a desktop computer. And do you think that's correct, or what's your theory of what that person looked like? So so if you didn't know, and if that's what Anne said, how confident would you be that she was correct? And keep in mind that, when you've probably read studies in sociology class or somewhere, that people are pretty bad at, remembering and being a witness for anything. But let's say here's another person, and she says that person in that first video had no glasses, headphones, and it was a woman that was sitting at a laptop. So now we have two instances of headphones, so maybe we're a little more confident about that headphone thing. But one person said it was a woman, and the other person said it was a man, and one person said it was a desktop computer, and the other a laptop. So maybe there was some computer involved, but our confidence is growing about certain features. And now here's yet another person, and that person says, hey, that first person had glasses, was wearing headphones, had a red plaid shirt, and was a woman. So as we get more and more people involved in this witnessing, our confidence might grow about what features were true about that first picture. And here is that first picture. And as you can see, the idea is that a group of people saying something, we have more confidence in that group than if only one person said something. So if one person at our job said, hey, we have off on Monday, it's a special event that our company's doing, maybe you wouldn't have much confidence in that report. But if more and more people are saying that throughout the day, either they're trying to trick you or your confidence would grow that you really do have off on Monday. And here's Mary Spender, and one of your friends said, hey, I think you'll really, I know what music you like, and I think you'll really like the music of Mary Spender. Maybe you think, maybe, but I'm not absolutely sure. You wouldn't probably go out and listen to her. But if a bunch of people said that, a bunch of independent people who don't know one another, they just independently told you that, you'd really like this Mary Spender person, your confidence would grow, right? So that's kind of the intuition we're using here, that a crowd can be more confident about something than one person. So as we group people together to make a decision, Supreme Court or whatever it is, we're more confident about that body than if only one person uttered it. And so now the question is, knowing that kind of intuition about people and knowing our definition of a weak classifier is one that's just a little bit better than chance in classifying a task. So if we're only looking at a yes-no type classifier, let's say that classifier is only 60% accurate. The question is, can we take a bunch of these weak classifiers and combine them to make a strong one? So can we create, all these classifiers are only 60% accurate, let's say. Can we do something that would make a classifier that's 99% accurate? That'd be pretty cool. So let's just look at a simple case of having a group of 3 classifiers, and they're going to vote on something, yes or no. And so if 2 vote yes and 1 votes no, we'll take the yes classification. So here's the data we're looking at, and let's say on that data, this was the error of that first classifier. That area in green, it made, I don't know, that's maybe 20% error. I'm not good at visualizing this. Here's classifier 2. It also makes the same amount of errors, 20%. And finally, classifier 3. Now, the important thing here in this initial example is these error bubbles are all disjoint, meaning that if we combine these three classifiers, we'd be 100% accurate, even though each individual one was only like 80% accurate, right? So here's a case of the power of even three classifiers is better than the power of just one. Of course, they're not always going to be disjoint. So here's a case where some of the errors overlap. And the critical part is that one, where there's a case where two classifiers are wrong, at least two classifiers are wrong, but that's much smaller. That area of error is much smaller than the error rate of one classifier. So the answer is yes, we can build a stronger classifier from a collection of weak classifiers. And all these classification methods that aggregate the votes of classifiers or aggregate a number of classifiers, they're called ensemble methods. So that's just a general term, meaning we're taking a number of classifiers and combining them into one. So now let's turn our attention to one type of ensemble methods called bagging methods. There are a number of different ones of these that I'll cover, but the general term is bagging. And for sake of illustration, let's say we have some data, so 1,000 rows of data, so a fairly large data set, and each row has 1,000, or there's 1,000 features for each instance. So bagging is where the classifier is built from a subset of rows selected randomly with replacement. And that with replacement is important. That's what distinguishes bagging from other methods. And what that means is that, let's say the training data for one classifier includes instance number 101. That instance 101 is likely also to be picked as being the training data for another classifier, right? It doesn't rule out that. So that's what bagging is. Pasting is the same thing, but without replacement. So if a classifier if the training data for a classifier picks instance 101, so that's included in the training data for classifier number 1, 101 can't be used in any other classifier. So that's without replacement. So that's bagging and pasting. Those are the most two common types. Random subspaces means that instead of looking at random rows of data, we're going to select a random subset of features. So we have 1,000 features in this example, and we're just going to select, let's say, randomly 500 of them or something for each classifier. So again, we can say with replacement, without, but that's what random subspaces are. And finally, random patches means anything goes. We're going to select a subset of rows and a subset of features. So those are the four main types of bagging algorithms: bagging, pasting, random subspaces, and random patches. Right, so the example looks like this then, where we take a large amount of data and we're going to divide them. We're going to get a subset of this data for training for each of the classifiers we're building, and that's the ensemble that we're developing. So let's take a look at an example of this, of how we would do it in code. Okay, so let's see how we can implement bagging and pasting and these other algorithms. The template I have here is kind of roughly how to follow it. So we're going to import the bagging classifier from sklearn-ensemble. The next thing we need to do is these ensemble methods have an ensemble of base classifiers of decision trees. So we need to create that. That's the next line, the CLF equals tree decision tree classifier. And we typically specify a max depth here. We don't let these trees grow to their maximum possible. And the final part of the little template is we group these together using a bagging classifier. And the final bit of the template is that we group them together using a bagging classifier. So that CLF in the argument is that base classifier. The n estimators is how many classifiers we're going to construct in our ensemble, and that n jobs equal -1 simply means use all the CPU cores that are available to perform this task. The next thing I have there is that handy table which implements what hyperparameters need to be adjusted in order to implement these different algorithms, whether they're bagging, pasting, random subspaces, or random patches. One option is the maximum samples column, and I describe it just below that table. So the maximum samples can be an integer or float. If it's a float, it just means a percentage. How much percentage of the training data are we using to train each classifier in the ensemble? So the default is 1.0, meaning use 100% of the data for each classifier. If we have something like 0.5, that means 50% of the data is going to be used to train each classifier in the ensemble. If it's an integer, we would use that exact number of instances to train. So if max samples equals 100, each classifier in the ensemble would be trained on 100 random samples from the training data. Max features, that last column, is similar. It's how many features are we going to use for training each classifier in the ensemble. Again, it's integer. It works exactly the same way. So it can be integer or float. If it's float, it's what percentage of the features. 1.0 is the default. So by default, we are training each classifier on 100% of the features. We might have 0.5. If we have an integer, it would be the exact number of features. So if we have 1,000 features and we say max features equal 100, each classifier is going to randomly select 100 features from that 1,000 to be used to train that classifier. So the middle column is Bootstrap, and that is whether or not we do things with replacement, and that distinguishes bagging from pasting. So with replacement is going to be Bootstrap equals true. Without replacement, Bootstrap equals false. There's a column I didn't put in. Let me get that, is Bootstrap Features, which is the same approach for the features. So if Bootstrap Features equals true, we select features with replacement, false without replacement. And the default in that case is false. All right, so with that underway, and keeping in mind this nice table on the top, which will help guide us in determining what hyperparameters to adjust for implementing different algorithms, let's go look at an example. And in this case, we're going to use a clothing example. We're going to use a medium-sized data set. And I don't know whether to call things medium or large. It's impossible to know in this how to categorize a data set. So let's just call it a data set. 60,000 images of really small pictures, 28 pixels by 28 pixels of grayscale, and these are different articles of clothing. So that's the example. This other picture is just kind of whizzing around, showing how this looks in a multidimensional space. Okay. And what we want to do is the classifier is going to look at this picture, this 28 by 28 pixel picture, and give it a label, one of 10 labels. Is it a t-shirt, a trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, or ankle boot? And keep in mind that if we just had a classifier that performed random guesses, we would expect the accuracy to be 10%, right? Because there's 10 categories. The features, again, are 28 by 28 pixels, or 784 features, those which are pixels, and they're grayscale values, 0 to 255, 0 black to 255 white, and the numbers in between are different colors of gray, or not different shades of gray, I guess. And the first thing we're going to do is just import that, and it's a bit boring, so I just wrote the code already. And this is a medium-sized file, so it takes a little bit of time to load. And there it is, and we see the results, right? We see that these, we have all these different pixels. And ahead of time, if you looked at my code here, I divided it into the features, which are these pixel values, and the label, which is a label column, which I'm not showing here. So it would be one of those 10 values. And you see all these pixels are kind of in a row. There's like 784 of them as I scroll over there. And if I wanted to look at one of these pictures, remember the picture is not just a row of pixels, but it's an array of 28 by 28. So I made this little function so we could see what it looks like, and that's here. So one thing I needed to do was take that row of pixel values and reshape it to be 28 by 28. And here I just select some random pictures, right? There's nothing special about them, but let's just execute that. And there we see what they look like. So again, they're 28 by 28, so they're kind of grainy, but some of them don't. I guess if I made the pictures smaller, maybe they would look a little better, but you get the idea of what we're trying to do. So if you looked up here at these values, and you can see that, again, I mentioned they range from 0 black to 255 white. And a lot of machine learning algorithms work best if the values are floating point between 0 and 1. So the first thing we'd like to do is convert those values from 0 to 255 to 0 to 1. So let's go ahead and do that. Let me scroll. And I'm going to call it close x, which are the features, f for floating point equals. So my original array was close x, and I'm going to divide that by 255. All right, and once that's done, I'm going to divide into training and testing. I have that code as well. So I'm dividing into the training features, the test features, the training labels, and the test labels. So let's go ahead and execute that. And you can see that, it indeed divided by 255, and now I have a nice test set of 48,000 instances, 48,000 pictures. And one thing we'd like to do is when we're looking at more complex classifiers, it'd be nice to know, well, can we just get a ballpark of what a general, easy classifier would be like? And for our example, let's test that with a decision tree classifier. So how well can this work with just a plain old ordinary decision tree? And so here I created one. So it's just, I don't specify max depth, so it's going to go down as far as possible. And I'm going to time it, even though this shouldn't take too long. I think this is definitely will be under a minute, maybe more around 30 seconds. Okay, that didn't take too long. So it's trained. Now let's fit it to see how, let's make predictions and see how well it does. So let's call it, base predictions equals, oops, oh, that isn't equals. Sorry. Okay, and we see it's 79% accurate, 79.72. Let's give ourselves a few extra points. So that's pretty good. I mean, remember that random classifier would be only 10% accurate. So actually a decision tree classifier is not that bad. All right, and let's see how that bagging classifier would work. So let's go through our template. So let's create a base classifier that we're going to use. So we're going to make a collection of these. So we'll start with what we're doing. And we are going to set a depth. Let's say it's 20. Then we'll import the bagging classifier. Oh. It helps to spell sklearn correctly. And I'm going to finally create one. The max samples, let's do 50% or 75%. We're going to make it bagging, not pasting. And we're going to use all the CPU cores. Yeah, I think that looks good. Let's give it a shot. All right, that looks good. And now let's fit the bagging classifier. Let's time it. That's, of course, not necessary, but I just enjoy timing things, apparently. Fit. All right, and this may take a little bit of time. Maybe it's a good time to get some coffee and or tea. Okay, and we're done here. You can see that it took about 13 minutes. And now for the exciting part, how good is it? Let's do that task. Oop, should have added the accuracy part, but oh well. Let me just add a cell here. And we get 87% accuracy. So that's significantly better. Remember 15 minutes ago when we ran it originally, we got 79.725% accurate. So significantly better. All right, and let's give pasting a try. So my first question would be, before we actually get to the code, is why doesn't this look good? What's the problem with this? And I'll give it a second for you to look at. Okay, and I'm thinking, I'm hoping that you got an idea. So in pasting, remember, we do random selection without replacement. If we have 30 estimators, then we couldn't get each one to have 50% of the data if we didn't have replacement. So that's why, these two, the max samples and estimators and bootstrap equals false, kind of collide into some nonsensical solution. So let's see if we can do better and use a little bit more common sense in developing this. And we're going to start with that CLF. Let's go with n estimators to be 25. This will make the math work out a little better. So the max samples should be 0.04. So that should give us 100% of the data. We're not going to do bootstrapping. That's what creates a pasting classifier. And the n jobs. Let me just look this over. And estimators, max samples, bootstrap. That looks good, I think. Okay, and now the time-consuming part. Well, in this case, I don't think it'll be that time-consuming, but let's give it a shot. Okay, that was a lot faster, and let's see how accurate it is. So let's call it paste predictions. Okay, still better than the general one, which was 78 or 79, I can't remember. We had 84% accuracy, not quite as good as our bagging classifier. And finally, let's skip random subspaces and try random patches. Okay, let's create one. Let's call it the patch classifier. Okay, CLF. Let's go with 25 again. Let's do with replacement and use 60% each time. And let's do the same with the features. And so bootstrap will be true. And bootstrap. spell. All right, so we're building a bagging classifier. The base classifier is that decision tree we mentioned. We're going to have 25 decision trees. Each decision tree will be trained on 60% of the data with 60% of the features with replacement in both regards. So I don't think I hit return there. Okay, this should also be quick, but I'll time it anyway. Okay, and that time it took 3 minutes and 29 seconds. Not too bad, but the real proof is how did it do? So let's do that. Patch predictions. I'm kind of obvious in how I name things. $87.225, and I don't remember what we got for the original bagging, so I'm going to go up 87.266. So basically the same accuracy. So of course I only kind of demoed things. I didn't investigate using a grid search or anything to find the best hyperparameter values. Maybe max depth could have been a little deeper or less deep. Maybe I should have used more max features or fewer features. Who knows? But at least you get an idea of how the algorithm works. Thanks so much for watching this video. I hope it was somewhat helpful. See you in the next video. I think we're doing an sklearn video, and then we're going to move on to deep learning. Thanks so much. Take care. Bye.